Also, welcome to lecture number 5. It's the 25th of, we are in Germany, of November 2025. Lecture number 5 in Introduction to Lattice Boltmann Models. And today we actually get close to the real thing, yeah, then we still need, of course, always boundary conditions and so on, but now we get to actually close to what we want to do. But before we get there, we have to discuss one question that is of primary, sorry for my, was not arranged here. That's a general concern when we discuss the Lattice Boltmann method, and probably some ammunition that you would need if you come to defend this to somebody. Yeah. So usually, if you actually come to people who understand what the Boltzmann equation is, which are not that many people even in fluid mechanics, they will typically challenge you with this idea of the Lattice Boltmann method, because the Lattice Boltmann method, as we saw, is derived only to solve the Navier-Stokes equation, and not the Boltzmann equation. Yeah, so we are not solving the Boltzmann equation, we are solving the Navier-Stokes equation. And if you want to solve the Navier-Stokes equation, why don't you just solve the Navier-Stokes equation? Okay. Now you could say why not, but the argument that will come up, so, or the question that is actually coming up is whether it's a good idea to use a kinetic method, whatever kinetic method, so in this case the Lattice Boltmann method. Okay, kinetic methods to solve NS Navier-Stokes equation. And by the way, the Lattice Boltmann method is not the only numerical method that uses the Boltzmann equation to solve the Navier-Stokes equation. Yeah, so there are others, for example, gas kinetic scheme, unified gas kinetic scheme. So they are, there are other methods that are based on integrating the Boltzmann equation with their primary goal being to solve the Navier-Stokes equation. So the reason why you may get challenged and asked why this is not a good idea is because you would have to resolve the particle collision or the particle collisions, yeah, if you use the Boltzmann equation. And now you can do this back on the envelope calculation. So I guess we mentioned what the mean free path in air roughly is. Mean free path in air, that's roughly 16 nanometers. Then you'll have the speed of sound, CS, so what is the speed of sound in air? 340 something meters per second, roughly. So now you have to resolve the mean free time. So viscosity, there is a small discrepancy between the real kinetic theory and Lattice Boltmann, because the terminal velocity is not identical to the speed of sound directly. But in Lattice Boltmann, it's due to the discretization, it's a little bit different. Here we just have the simple relationship that the viscosity is speed of sound times times the mean free path, yeah, or so yeah, and in reality there's a factor of order 1 in front of this. It's actually, I believe it's square root 3 or something, yeah. I mean, for an ideal gas, we would have to say, because in reality we have to consider the internal degrees of freedom for the speed of sound, and then you have an adiabatic coefficient that changes this, and actually this relationship between viscosity and speed of sound is dependent on this adiabatic coefficient, and it will be different for monoatomic molecules and, for example, nitrogen, yeah, and other things that have more atoms per molecule. So more internal degrees of freedom. This is where it depends on, yeah, because internal degrees of freedom carry energy and modify the movement of energy then. So this is our speed of sound. So we have a mean free time that's roughly lambda by Cs, and now you can do this calculation and you get to 0.17 nanoseconds, and this is often considered to be short, right? So it looks like you would have to resolve this, and I mean, if you have to resolve something, then you have your time step would need to be much smaller than that in order to resolve this. And this is actually a problem that, depending on your discretization, you can actually have. When you discretize the Boltzmann equation with a standard. Okay, what is standard? So taking some sort of discretization, finite differences on the Boltzmann equation, or finite elements on the Boltzmann equation. Actually, we have these problems with finite elements on the Boltzmann equation. Then you would have to resolve this thing here. So, but Lattice Boltmann behaves in a different way, and this is sometimes, I've taken this out of the lecture because if you look at some of my older lectures, I'll talk about what is this called, the asymptotic preserving behavior of Lattice Boltmann. And the problem with this is that Lattice Boltmann is not properly asymptotic preserving, yeah. And so I take this out. But if you come along this if you ever heard this asymptotic preservation, means that if basically if you have a proper scheme, okay, well, now the consequence of this is if you solve the Boltzmann equation with Knudsen number going to 0, you can actually increase the time step to a larger value. But the real thing, okay, I didn't want to talk about asymptotic preservation, and then I will start talking about this. So you have to discretize, yeah, the Knudsen number and space, and so you have to transition from the Boltzmann equation to the Navier-Stokes equation, and then you also have to discretize both. And asymptotic preservation means that you get the same result no matter how you go. Like you're first discretizing the Boltzmann equation and then go to Knudsen number 0 leads you to the solution of the Navier-Stokes equation. Yeah, so you can draw a rectangle. Yeah, okay. I'm not going to draw this rectangle, but if you're interested in this, you will find some literature on this. So we want to be more practical here. Our BGK collision operator in the Lattice Boltmann method had the following. So this is a little bit a repetition of last time, but I repeat this. I don't repeat a lot, but I repeat this because it's very important. So we said that our collision, omega, is the difference between the post-collision and the pre-collision, which we write like this, right? And this, in the Lattice Boltmann method, is written by this relaxation parameter omega. By the way, I have to watch out whether we have the mic running. The mic is running, yeah. So of the equilibrium function minus, and this is again important, the pre-collision state. Yeah, and I remind you of last time that the pre-collision state is not the state where we solve for. Yeah, we solve our discretized Boltzmann equation for the average between the pre and the post-collision state. Yeah. So now the thing with this is that if you look at this and we take the this Fi to the right-hand side, yeah, then we get explicitly the post-collision from the pre-collision, which means this is the algorithm that we actually apply in the methods. This is explicit. So you will often hear that Lattice Boltmann is an explicit method, and this is by some people considered to be an advantage. So if you tell a mathematician, applied mathematicians, that you apply explicit methods, that they think you're insane and you don't understand anything. Yeah, you're just stupid, and they stop listening to you before you finished your sentence. Yeah, so computer scientists or people who try to, get things done. Yeah, they like explicit algorithms because they just run fast on a computer. Yeah, in fluid dynamics we have this problem. We have these immensely large systems, and we also want to run this. So because we have these insanely large systems, we want to solve our equations in parallel. So there is something to, so of course you can solve implicit equations in parallel too, but whenever you solve an implicit equation, you have the problem you don't know how many iterations it takes. Yeah? And then you don't know a priori how to distribute your work. Yeah? So if you have an explicit algorithm, you always know a priori how long it will take to do certain work. So you can easily and very, very, very efficiently distribute it over immensely large systems of computers, parallel systems. Yeah? So, and a few other advantages if you have an explicit algorithm. But the mathematician will tell you that's not a good idea because this requires small time steps, and small time steps is what we fear here. Yeah? So, why is this not a problem? So this is not a problem because we are actually solving for this. So we have a change of variables. By the way, first introduced by her. I don't know how this is Chinese is correctly pronounced. He is not he. I mean, it is a he, but he is not called he. Her. Yeah, something. Okay, I met him once in my life, I believe. He's an older guy. Yeah, so he first made this change of variables. Of course, he called this in a different way. So for him, this f without bar, the pre-collision was the one with bar. And okay, yeah, I kind of missed this. This was before my time. Yeah, so just for practical reasons, we rewrite this in this way here. Yeah, so we can just rewrite this, and then we can write the collision up there. So this guy can write this like this as omega Fi equilibrium minus Fi average minus Fi minus Fi asterisk, so after collision. So now this is an implicit equation, yeah, because you see the post-collision depends something on the post-collision, right? So changing the variables made this an implicit task. So we actually get the collision operator depends on not on the difference that it had before collision, but before and after collision. Yeah, so implicit, and this implicit behavior, this can be removed by bringing this to the other side, which is again the repetition of what we already had last week. And then this thing looks like this. And then we have what we actually solve for. And this thing is in fact implicit for Fi over bar. Okay? So actually we have an algorithm that is explicit, but this explicit algorithm solves for something that does not exist in our algorithm, namely this average, but that is the actual true solution. And for this, it is implicit. So since this is an implicit way of solving this Boltzmann equation, we have no stability limit on collision time. And this is what we want to have. So it is not, because we have an implicit integrator for the collision, there is no reason why the time step cannot be larger than the collision time. Yeah? So the collision time, or the mean free time, would then be written as 1 over omega minus 1/2 times the time step. And our implicit collision frequency is therefore, we write this the other way around, delta t divided by the physical mean free time plus 1/2 delta t. So, and this is implicit VGK. So now I have to tell you something again. I'm always sorry that I sound so old to me when I tell you stories from what I've seen through the decades, I have to admit. Yeah, really decades. Going to conferences in Lattice Boltmann. So every so often, I think it has become less common in the last 10 years or so, but like the 20 years ago or so, 15 years ago, going to conferences, you often discovered a poor young PhD student from the mathematics department who had looked in this strange, who were told by their professor to look into this strange method. Yeah? So then they discovered that this is very primitive and is apparently using Euler forward as an integrator, and then they decide that they as mathematicians know better, and I see this repeated and repeated and repeated again. So they as mathematicians know better, and they know better how to integrate then with Euler forward. So they do a proper finite element discretization of this Boltzmann equation, And what they end up with is the proper discretization of the Boltzmann equation, where, of course, this annoyance of 1 over omega minus 1/2 is removed. Yeah? And they have it properly, they have it correct. Okay? So they come up being very proud, because their omega in the explicit version, when you do this kind of discretization, is delta t over tau, and this is this becomes then an explicit scheme, which of course you can, like you can also try to solve this in an implicit manner then later. Yeah. So then they are proud, and they run their simulation, and they get good results, and then they see that they don't get scalability, and then somebody has to tell this poor person, well, you really shot in your foot. And you know, the problem with this is the PhD students come about, do this, try it out. After 1.5 years, they notice that there is no use in this, then they abandon this, write no paper, and the next one is doing the same thing again. Yeah? So therefore this kind of warning here. Yeah? So remember, what is the problem? The problem is that we like to have delta t, the time step, much larger than, you know, the collision time between these nanoseconds, yeah, the 0.17 nanoseconds between particle collisions. Yeah, we want to have larger time steps than this, very obviously. So if you look at what this means when delta t is much larger than tau. So what does it mean from a practical point of view for our implicit case here? So say we make this. So basically we let tau vanish in comparison to delta t, yeah? And then what is then the outcome? It's 2, right? Yeah? So, and what happens in the explicit when you make tau vanish? This is going to infinity. Now, how do you implement this? Yeah, so it's not even surprising that this doesn't work. Yeah, I mean it is very natural, very obvious that it doesn't work. Yeah. So, I mean one thing that's a little bit of interest here is if we look at what happens when we set this thing to 2. So this is our collision operator, yeah? And now suppose we set omega equal to 2. So if we set omega equal to 2, we have, of course, Fi after the collision is Fi before the collision plus 2, Fi equilibrium minus Fi before the collision, which is equal to Fi, those 2 Fi equilibrium minus Fi and Fi. So, okay, so you can very simply exchange these two to see that this is Fi is equal to 2 Fi equilibrium minus Fi before collision. So why I'm showing you this? I mean, first of all, it is the case for omega being 2 is the case of viscosity being 0 because tau is 0, right? So first of all, it is mathematically not entirely unfeasible. We don't observe that this is necessarily stable, but it's not obviously unfeasible to do this, to put viscosity to 0. Yeah, and viscosity to 0 means Reynolds number, I mean, asymptotically, Reynolds number to infinity, right? So that's not completely unfeasible. So we can say it is well conditioned, so there are no strange numbers. You don't divide by 0 or something, yeah? It is well conditioned. For delta tau is much larger, delta t is much larger than tau. And the other thing that you see here is, so if this is the forward in time, yeah, we are back to Boltzmann's ether theorem. Yeah, this is forward in time, so this is backward in time. Yeah, so no viscosity means reversibility. Yeah, and actually, you see the reversibility here. Yeah, you can exchange going forward with going backward. I can tell you this is not stable, yeah, but at least it is recovering this this property. Okay, we'll give a name to this, which you have maybe heard somewhere else. You may have heard about what is the successive over-relaxation for some numerical schemes. So this is actually what we are doing here. We are doing over-relaxation. So this regime where omega is larger than 2 and smaller than 1, is smaller than 2 and larger than 1, this is called over-relaxation. And Lattice Boltmann exists only because we have this over-relaxation. Yeah? So if we started with this, if Lattice Boltmann came up with this, we wouldn't talk about it. Yeah? The only reason why we talk about Lattice Boltmann is because it looks this way. Yeah? Because this means we are not bound by the time step of collision. So there is no efficiency penalty from using kinetic methods. Okay, there is a picture I'm liking to draw. It will be very ugly as always. So, the state of one lattice node has many dimensions, as many dimensions as we have velocities, obviously. Yeah, and this can be placed in their different moments. So unfortunately, it is not easy to draw this. So when we draw things, we can only indicate things by drawing them in 2 dimensions. So there is an M1 and an M2 as from 2 different moments and 2 different non-conserved moments. Yeah, and this is of course completely cartoonish, but I hope it will still be useful. So say we have our equilibrium state for given as a point in that space, right? Then we have, together with this, our incoming state, F, here. So there are 2 different points in the same space, and this space has many dimensions, yeah? But we draw only 2. So then, let me see that I'm not making it completely ugly. So 2 points here, 2 points there. 2 points there, something, okay. You see, I'm trying to draw a circle. I'm really, so this here, just right to it, is supposed to be a circle, okay? So, like this, yeah. okay, the meaning of this contour that I draw on the circle could be, and then maybe it may not be 100% a circle, but it will be a convex shape. Yeah. So saying that when we talk about entropy, actually this is supposed to be on the line. When we talk about entropy, yeah, then this would here be, for example, the contour of all the entropies, yeah, that has the same entropy as the incoming distribution. Meaning that now, depending on how we define entropy, positive or negative, say going to the equilibrium increases entropy, yeah. So then entropy inside the circle will be smaller than everywhere, and outside it will be larger, yeah. So collision will, because collision will drive us to higher in entropy, the outcome of the collision would be some point inside that shape, which is approximately a circle. Yeah. So how it can be any point inside, basically, in order to reduce the to increase the entropy. Okay, however you define it. Yeah. So now any point. So how do we do this in BGK? BGK is a very strong simplification by saying we do an interpolation between this incoming state and the outgoing state. Yeah. So and usually if we had an explicit method, we could only use this range from before to equilibrium. Yeah. But when we use over relaxation, we can also go to the other side, yeah, and stay here. So for example, we do over relaxation to this point. So this here would be an over relaxed solution. Where we could also have in a different setting, when we go to this here, this will be under relaxation. So, and over relaxation means omega is larger than 1, and under relaxation means omega is smaller than 1. And this process is linearly stable. This is a big but, linearly stable when omega is an element including 0 and excluding 2. Linear stability means the equilibrium. Okay, I have not written F here. So because the equilibrium is a nonlinear function, so this doesn't necessarily translate to the real solution, because unfortunately, we deal with a nonlinear system. Yeah? There are linear lattice Boltzmann methods, for example, in solid mechanics that my colleagues in the ETH Zurich is just developing, and they work with omega equal to 2. Fluid dynamics, omega equal to 2, no go, will not work, okay? So what is the problem behind this? So is lattice Boltzmann unconditionally stable? No, unfortunately not. Because even though the collision is stable, the entire method is not stable. It's conditionally stable. Sorry. Because we have, funny enough, we have a limit on streaming. And this is the famous CFL condition. So, is it required to explain, does anybody not know what the CFL condition is? I think last year the CFL condition had its 100th birthday. I think it was, the paper was, okay, you find out. I believe it was 1924, yeah? The paper. Courant Friedrichs Levy, yeah? Published this paper. So what is the CFL condition? The CFL condition just means that information cannot move fast. Okay, the physical information cannot move faster than the information moves in the numerical scheme. And this is for solving, for example, the Navier-Stokes equation, a problem due to the nonlinearity, because you can physically have shake-up, right? From like a combination of eddies that just add together that you get a turbulent burst. So there is actually no physical limit that you suddenly get higher and higher velocities. Yeah? And because there is no limit on this, the method cannot be, on principle, unconditionally stable when it has a finite speed. So the idea behind this is, suppose u is the magnitude of u is the velocity of the fluid, and to this velocity of the fluid you have to add the speed of sound, yeah, because you have what's that called, when something is coming, the Doppler effect, right? So you have a Doppler effect. So the speed of sound is, so if the fluid moves, the speed of sound is added to this, yeah. And so you have pressure waves that go in the direction of the flow, and this has to be slower than the information that you can move. So you have an advection term, and you have an acoustic term. So, and usually we are done with this, and there is one more term that I have to admit I'm a little lazy here, and I'm not completely sure. I believe there could be a prefactor because I have not derived this. I just mentioned this. This is usually not of concern in the cases that we are dealing with, but it may be of concern in a different direction. This is the diffusion term, and this is somehow related to the momentum flux due to a gradient in velocity. Yeah, so momentum flux. So this also there's also momentum flux that is added, yeah, to the moving fluid due to viscosity. Now, usually this thing here is extremely small, such that you never consider this in practice. Just for, you could have the case that you have a very, you can run, leaving this out is just not true. You can increase because this would imply that you can increase the viscosity arbitrarily, and this is not true. If you increase the viscosity arbitrarily, you will crash it because of having too high viscosity. Yeah, that's also possible. So there is a upper limit to viscosity, which is usually not on our concern. So all of that together must be smaller than the crit spacing divided by the time step, yeah? Meaning that delta t must be smaller than delta x divided by u plus cs, and the other thing here you may just forget. And I may have, I've not derived it, so there may be a prefactor that I've forgotten, yeah? So, but the other one is clear. Yeah, this is a very. This is how Lattice Boltmann always becomes unstable, even if other things make it. I mean, initiate the instability, yeah? The actual instability occurs when the velocity is getting too large, and once it crosses this value, it blows up immediately. And this is very hard, you really see this is a very high boundary. Right, so, okay, having written down some numbers here, so for example, if we have a delta x of 1 millimeter, and say we are just concerned with CS, so say velocity would be 0, then, I mean, usually usually your velocity, because we do a small Mach number assumption, right? Yeah, so this implies that U must be much smaller than CS, not necessarily for stability, but for accuracy, because this is the assumption under which we have derived the Navier-Stokes equation. So if this is not the case, you are not accurately solving it. Yeah. So anyway, this means that you could usually assume that U is small and that the CFL condition is governed by CS, right? Then this means that delta t could be 3 by the power of minus 6. Of course, if you have a larger delta x, this will be becoming even larger. And this is, of course, now already much larger than what we would have to resolve if we used the mean free time. So then, in practice, we can have even larger time step, and the reason for this is because what is in practice done is rescaling the Mach number. So this is just what is done in practice, especially these guys who are doing wind turbine simulation. They never use the right Mach number, I believe. So I reckon that so they always run their wind turbines at Mach 0.5 something, right, around.
I've been running them under various Mach numbers by now.
Okay, good choice. Yeah, so rescaling Mach number gives you even larger. So this means because we assume Mach number is relatively small, we don't take the correct Mach number, but we take a Mach number that's slightly larger than what we have in reality, and then we can then we can have larger time steps. So this doesn't work when you work with acoustics. When you're dealing with acoustics, then you have to take the right Mach number. Okay, so I'm saying this again, but LBM is efficient only due to over-relaxation. Yeah? So this is the reason why we are here. And because, I mean, this time, this CFL time step constraint is basically the same, physically the same, that is also present in an explicit Navier-Stokes solver. So this means that in practice, the so in principle, this means that from an efficiency point of view, at least what's about time step to grid spacing, yeah, it's basically the same as Navier-Stokes, which also means I often hear that it's better than Navier. That's not true. It's the same. Okay. I mean, it may be easier to parallelize and it's faster for that reason, but it's from a purely mathematical point of view, it's really very, very closely the same. Yeah. So nature there is a conservation of complexity. Yeah. So if you solve there are several ways of solving a problem, but if you make it if you remove all the inefficiencies, yeah, you end up with very similar qualities, right? That's conservation of complexity. Actually, this is something that Stephen Wolfram talked about when I had the only time when he was on one of these conferences. You're making a note, yeah. This was a very strange, it's very strange talk. Sorry. I'm losing my. Yes, this is what I wanted to say. So when we, it's also important, yeah, there is no, please, no magic thinking, yeah? There is no kinetic physics. So there is no additional physics if you do not resolve them. If you do this, your Knudsen number square is 0, right? So if you take the time step much larger than 0, yeah, there is also I mean, you can prove me wrong, yeah, but then you also have to prove it to me that you recover anything from the Boltzmann world into the Navier-Stokes, into the Lattice Boltzmann world if you are not resolving it, yeah, would be very strange. So no magical thinking, please. So then is there anything cool, anything that we inherit from the so-called kinetic legacy? There is one thing that we actually inherit from the Boltzmann world, and this is we have a linear advection operator. So this is something that's actually really useful, yeah? So our advection operator is linear. The advection operator is a non-local thing, also in the Navier-Stokes equation. So in the Navier-Stokes equation, if you have a Navier-Stokes solver, you have to deal with the non-linearity and the non-locality at the same time, where in the Lattice Boltzmann method, you have all the non-linearities in the collision, so they're all local, and all the non-localities are linear. Yeah? So that's actually what we get out of the kinetic theory here. So having said all of that, let's go to the actual model. So we want to have a discrete, we need a discrete equilibrium. Okay, why do I have this heading? Discrete equilibrium function. And for this, of course, we also have to have a discretization of our velocity space first. And we start, as in your homework, with this being, let me see how to draw this. So now last time we had this one-dimensional thing, which was not very useful. Let's do it two-dimensional. Yeah, and regarding the first, okay, maybe how much time do you have today? So regarding the first lattice gas automaton by HPP, Haslacher Pumo, I don't remember. So the first that didn't work, I think it was 73. That had a velocity distribution like this, and for some equations, this is a sufficient way to do this. Yeah. So, we had this one-dimensional case that f. Now we use two indices, f1, 0, yeah, for the x world and one for the y world. So these are Miller indices. Yeah. So they are useful for multiple dimensions. F, what is this, 0, -1, and 0, 1. So this was the first thing in actually the 70s, before I was born actually. Yeah, so I was born in the 70s, but not at the beginning of the 70s. And this didn't work. So this didn't give a solution of the Navier-Stokes equation. And the first thing that lattice gas was actually supposed to do is to find out what are the criteria on the velocities that you get the Navier-Stokes equation out. So this was a physical toy model. Yeah? It was not supposed to solve some equations at first. And here we saw that this didn't work. So the solution that was come up in then 1985 by De Humière, I believe, and actually published by others. So, for example, by Wolfram so I mean, the one talk that I heard by Wolfram in person was that, I mean, he complained that this was stolen from him, which everybody in the scientific community is absolutely sure is not true. Yeah, because there's actually there are these odd French papers by De Humière showing that he has done this long before. The thing with this is it was not first published by the person who invented it, and this is a little bit unfortunate thing. Yeah. Okay. So they had a little bit a different solution. They used a hexagonal lattice. Yeah. But this is now outdated. What we are using is we are using something that is a so-called projection of a four-dimensional phase center hypercube. Okay, I don't want to explain how this came about, but you know, as I said, the way up a mountain is very, very strange at first. Yeah, the problem that they were facing is they did not like to have different weights associated with different velocities. Yeah, so what they wanted to have is that all these arrows would have the same length, so the same energy, right? So now you see this is not the case here. If you draw this in 4 dimensions, then they would all have the same. So then in 4 dimensions you can draw one that has all the same energy, and then you do a projection down to 2 dimensions where several of them collapse onto each other. Yeah. And then the difference, so they would have the same energy in 4 dimensions. Of course, in 2 dimensions they don't. But since now they collapse in different ways, some of these directions would add up more. So there are more 4-dimensional directions than others. So this direction here comes out as having more 4-dimensional directions than this one going up here. Yeah. So again, if you're interested in history, you can draw this out of some drawer somewhere. Yeah. So this is not the modern way of thinking. This is F11, F minus 1, 1, F minus 1 minus 1, and F1 minus 1, and also we have 1, 0, 1. Yeah, F0, 0. So this is something that we can use as a discretization, and this also comes with a name. It's called D2Q9. So somebody invented this nomenclature, and this is one of the most cited papers in all of Lattice Boltmann, just because of mentioning this kind of nomenclature. Yeah, you only have to invent a name, then you get cited. Yeah, that's so. How do we get now to our discrete equilibrium function? There are 3 ways that I want to discuss here, and the first one is also I believe good teachers always start with the stupid one so that people listen and then come to the good one in the end. I'm not a good teacher. I'm starting with moment matching. Moment matching. So we have 2 dimensions, so we use indices A and B, yeah, and for the F we have 2 indices I and J, and they go from -1 to 1, and we have here I by the power of A, J by the power of B, F, I, J, and we know that the conserved moments are always the same as they are in equilibrium. Yeah? So then we have to find moments of this, and obviously we have 9 independent moments for 9 populations, because we have 9 populations here, right? So our moments would be M00, that we call rho, M10, that is rho U, and M01, that is rho V. So these are the conserved moments. Yeah? And I hope you are now already familiar with this. So then we come to M20 equilibrium. This is also something that we have already done, so you can tell me, rho times U square plus CS square, right? So, and then M02 is obviously the same thing in the other direction. So then we have M11 equilibrium. You already know what it is, or do we? Rho VU. And the reason we discussed is that we have factorization of the equilibrium. So now we have, out of how many do we have? We have 4 conserved, 3 of them, so we are at 7. Right, so are we at 7? We have 6. What did I say? No, because we have only 2 velocities. We're in 2 dimensions. Yeah. So we are at 6. So we need another 3. So what do you suggest as another 3? Well, okay, we are countable moments. Count up. 30. 1, 2. Okay. 1, 2. So how do we get to 1, 2? Factorization, right? Equilibrium. So we don't need to write. Okay, I did this is for conserved moments. We didn't need this. So we've just seen this. So this is rho U CS square plus V square. Yeah. So and then obviously M21 equilibrium is rho V CS square plus U square. So and then we need one more, and if we count up, then okay, when we use, there are several reasons why we don't want to use 3, 0. But I give you only one. We want to have it isotropic. If we have only one left, and if you now take 3, 0, then you have no way to take 0, 3. So what would you take in order to be isotropic? 2, 2, right. So 2, 2 is again factorization. I mean, you are right in the sense that you are jumping to a forced moment, yeah? But you see, there is a problem, yeah? And the problem is actually, okay, we come to this in a few minutes. So where we are, yes. So this, okay, this is very obviously rho cs squared plus v squared times cs squared plus u squared. Okay? Okay, so now as you correctly saw, we get some third order, namely M30 and M03, three order in velocity. Terms are missing. So the order of the moments correspond to the the power of the velocities, yeah, and this is no accident, yeah. So what we are missing here is u cube, yeah, and v cube. But what we have is u square, v square, and this actually leads to an anisotropic equilibrium. So there has been in the past some discussions about this. So I all my life I spent with Lattice Boltmann. I use this kind of equilibrium that I moment match, and others use a different definition of equilibrium. And one thing that seems to annoy some people, and I've, for example, Pierre Lallemand, who is a big shot in one of the actual really inventors of the methods. He told me, I mean, they are all aware of this, but he told me he does not like to have this term here, because if you plot this equilibrium, it is non-isotropic. So if you draw the contours of this, you don't get a circle. Whereas when you just assume this term here is 0 and you drop it and only have second order terms, you get a perfect circle. Yeah? So he told me he doesn't like this because it's not isotropic. The thing is, I mean, he proved to me that also the error, therefore the error becomes anisotropic, whereas when you drop this term, the error stays isotropic. And the reason why I did not accept this as being useful is that even though the error here is non-isotropic, its numerical value is smaller than the error that you would have if you have the isotropic. So you can have an isotropic solution with a large error, an anisotropic solution with a small error. Yeah, and you can have some taste, okay? But usually we prefer to have small errors and try to go as best as we can. And therefore, that should be kept. And you see real differences, in particular in stability, when you keep this or you drop this. So, suppose you drop this, what you end up with? There is, so this up here you will usually not find that much in the classical literature. What you'll find in the classical literature is you find the Taylor expansion of the Maxwell-Boltzmann distribution or equilibrium. And this is Taylor expanded in velocity and therefore to second order usually. So this is something that you will find, for example, if you go to Wikipedia and look for Lattice Boltmann, then you will read there that you have Fi equilibrium is some weight. This is a W, not an omega, like in all the Chinese papers, yeah? W, rho, 1 plus, now this is a unit vector E. Okay, I hope I'm not making any mistakes. I've not derived this, I'm just writing it down. Maybe I don't remember, maybe I've taken it even from Wikipedia, I don't know. 2cs squared minus u times u divided by 2cs squared. Okay, because we are using, no, it's even, okay, it's even, the units are even consistent because we divide by cs, yeah. So this wi, so you see there's only one index here, yeah, because this is coming from literature, it's not, we use two, I use two indices here. Literature uses one index, so you have an arbitrary ordering, yeah, which I don't like. So these are weights, and you can obtain these weights by, the way I would do it, this is probably not the way it was originally done, but I would do it, get these weights by using the moment-matched equilibrium, set the velocity to 0 and rho to 1, and then you get to these weights. Okay? So usually I leave it with this and let you figure this out yourself, because I made the observation when it comes to the homework, then almost everybody uses this instead of this, even though I'm always saying please use this here, but I leave it to you because I'm interested in to see why again you are doing this, and then later I will ask you. I think the reason why everybody is using this is because if you are concerned with your homework, so some years ago you would go to the internet, download some Python code, see how it is implemented there, and you copy this or you take this and just use it. Nowadays, forget about this. You just ask, what is the newest thing? Anti-gravity, yeah, GPT-5. Write me a Lattice Boltmann solver, and out it comes. Okay, and it will usually come out with this, because this is what is in the textbooks, and this is what ChatGPT reads, yeah, so it will drop out like this, yeah, and I really encourage you to, do it by hand, yeah, but what can I do? Okay, you can implement both, and you'll see a difference actually, yeah. So what I just said, isotropic, this is what Pierre Lallement was pointing out to me. It is isotropic and it's missing higher order terms, so it's the highest velocity is square. This is equivalent to moment matching if you drop this thing here, yeah? If you do moment matching and you drop this, you'll get the same result. Observation is this is less, and significantly less stable than what you get out of moment matching. And there are other things, for example, dependency. The thing that you actually observe, I was talking about errors. The error that you observe is that you do not get the correct viscosity. Yeah? So the viscosity becomes a function of velocity. So we say the viscosity is not Galilean invariant. This happens in both cases because we have missing, and because there are these missing terms in the other way too. But the amount by which the error is dependent on velocity is much larger here than it is here. And the advantage with the Taylor expanded equilibrium is indeed that it does not depend on the direction. It's isotropic. So you have an error in viscosity, wrong viscosity, but the viscosity is not dependent on direction, whereas up here the error is smaller, but it's dependent on direction. I have one more. One more is the entropic, the so-called entropic equilibrium. Okay, if something is so-called, then this means that the one who is talking about this does not believe in it, right? We called the East Germany the so-called Democratic German Republic, yeah, and now the so-called, all these things in Ukraine and so on, the so-called, yeah, so the so-called entropic. So there is okay, I'm writing this down, and I hope I'm making this right because I don't know. So this pi is a product, yeah. So you have again the weights. You have a row, and you do a product over the dimensions that you have. So that would be either 2 or 3 usually, and here comes 2 minus something that's called what am I doing? S alpha, and this into 2 u alpha plus c. So this is the lattice velocity S alpha divided by c minus u alpha. So alpha is the direction. C alpha is the velocity in the direction divided by c, and c being delta, of course, delta x by delta t. So this is their nomenclature. And this thing that they call S alpha, so S by direction, is square root 1 minus u divided by cs square. And this is from Anzumali and Kali from Zurich. You know these guys? No. Okay, so 2005 or 6, I think 2006, something around this time, or even 2004. So this is supposed to be much more stable. One reason why it is more stable is because it also includes, because it's a factorization, it also includes the terms of forced order. So it is naturally more stable than the Taylor expanded. But there is one more reason why it's more stable. And the funny thing is, I mean, this was invented 20 years ago, and only the last 2 or 3 years, I have not talked to these people for a long time, but only in 2024, I learned that they actually explain why it's more stable. Yeah, and the reason why it is more stable, and they have not, even though it is in plain sight, they have not, apparently it was not obvious. So you are modifying, what you are doing here is you are modifying the speed of sound. Meaning you have an adaptive speed of sound. And when you have an adaptive speed of sound, meaning when your velocity is getting larger, your speed of sound is getting smaller. Yeah? And the sum, sum of velocity and speed of sound must be smaller than 1. So you make the speed of sound smaller, the larger your velocity becomes. Your CFL number, your CFL boundary is extended. Yeah? So this leads to the case that the CFL that we still have becomes U must be smaller then delta x by delta t, which I have to tell you this is of course nonsense, because this means that when you come to this boundary, you essentially put your speed of sound to 0. Yeah? So, physically you should not, physically this doesn't make a lot of sense, yeah? Because you're doing a Galilean transformation, and this leads to a different speed of sound. So first thing, the other thing is, what does it actually change? Because the speed of sound in the Lattice Boltmann method is around 0.5 delta x by delta t. Yeah, it's 1 over square root 3. Yeah, so it's in that range. So you double your CFL. That's all you get. Yeah, you can just double your time step, not more. And that's not, that's not actually significant. Doubling the time step is not significant. Yeah. But okay, so that's around. So these are the ways you can derive your equilibrium function. And now let us go to lattices in 3 dimensions. The real thing. And we always start with going in 3 dimensions. We start from 1 dimension, f minus 1, f1, and this is called the D1Q3. And then what we like to use is the so-called tensor product lattice. For example, D3Q. So now it's 3 by the power of 3. Yeah, so it's D3Q27. So this is the full stencil that you can have. So, and the question is, what moments does this support? What moments? So there are, of course, okay, I should probably do this on the next page. Yeah, it's okay, so we have the countable moments. So there is a zeros moment. This is M000, and this has 1 permutation, obviously. Yeah. Then there is first order moments that look like M100, and there are 3 permutations of these. Then we have second moments. I'm not writing moment again. The M200, 3 permutations. What else? So we have M110, and out of this, obviously, 3 permutations. Third order moments. No. Yeah. 111. Okay, 111. How many permutations? 1 permutation. And what else? 120. How many? 6 permutations of these. So then fourth order moment. So what do we get? M, give me something. 112. How many? 3. What else? 0, 2, 2. Okay, I'll write it 220. Yeah, 220. How many? 3. So then fifth. 1, 2, 2. How many? 3. sixths, 2, 2, 2. Now, and if you count them together, you'll get 27, hopefully, right? So, in order, that there's a cause of dimensionality. Yeah, so in the PhD defense I just left to come to the lecture, they were talking about the cause of dimensionality. So more dimensions, more moments, much more moments here. Yeah. So the Navier-Stokes equation require the full moments. Full moments means non-equilibrium plus equilibrium up to second moment. So we need all second moments. And equilibrium for third moment. So this is something that we derived 2 weeks ago, if you remember. So this means that we have quite a few non-essential moments. And these non-essential moments have an official name. That is, so it's really official. This is used in literature. They are called ghosts, ghosts or ghost moments. Okay. Daniel found out that CFL paper is written in 1928. That's the advantage that he has. That he is doing this online as a computer. Yeah. Non-essential. So they are called the ghosts. And ghosts are usually discussed as being a problem. So ghosts seems to be something negative, yeah? So ghosts are, why is this negative? It's negative because they waste memory, yeah? I mean, they are there. They are degrees of freedom that exist. You have to allocate memory for them. You have to move them around. And you don't need them. And that looks strange. Yeah? So they're often seen as a waste of memory. And also, that's not all. They are also a danger for stability. Because you don't need them, but they do something. Yeah? So if they become unstable, everything goes unstable. So this is why they are often considered a problem. They can also be your friend if you treat them well. So then there is, let me see how to get this. No, that's not arbeiten. Okay, I have a small picture here. Yeah, hope you like it. Unfortunately, I copied this too often. Now it does not look very nice. Yeah, I did not find the original before I started the lecture. So there are attempts to eliminate ghosts by pruning the lattice. So the one that we have on the left is the full discretization, and now you see they encompass. So they all have the zero velocity, which is not visible in this. Yeah, but if you look at this this cube, then this will include all the faces, the edges, and the corners. And now you can take this, what we call energy shells, because edges, faces, edges, and corners, they have different energy. So if you measure the length of the vector, they are different. So this is why they are called energy shells. And now you can eliminate some of these energy shells, and they will still have enough, they will still have the hydrodynamic moments left. So the most popular actually is the D3Q13, where we leave out the corners, and the D3Q15 used to be pretty common. I've not seen much of it in the last 10-ish years, where you leave out the edges. And then there's the D3Q13, where you only keep the edges. That's a very strange model that is very difficult to use for several reasons. Yeah, and you can make you can see maybe we'll okay. It is difficult to use. It is the smallest known symmetric representation to cover all the hydrodynamic moments, which are, by the way, 10. So this has only 3 ghosts. Yeah. So it's pretty close to the apparent optimum. So always remember the number of moments is infinity, right? So we can have infinitely many moments. However, the number of independent moments is the same as the number of the populations. So dependent moments, they also exist and they also play a role. Dependent moments. They are determined by what did I write here? By lower order moments. Okay, so what we usually do, you can of course choose which moment you want to have, but because the lower order moments, yeah, we have this moment hierarchy, yeah. So where we depend on, where lower order moments always depend on higher order moments. So you want to keep the lower order moments correct. So you say this is my independent moment, and then the higher order moments that depend on them, they are the so-called wrong ones, yeah. So because they give basically what you have the same information, and this is an alias moment, and because now this is an unofficial name that was coined by me, and I think nobody really picked this up a lot, but so just for the purpose of this lecture, because the ones are the ghosts, these are the aliens. Because they do some aliasing, yeah? I should probably write them aliens, I don't know. So, the aliens. So, for example, what do we have on this lattice? We have M A B C is equal to the sum over ijk, that's going from -1 to 1, over fij k, I by the power of aj by the power of b, and k by the power of c. Now you see that this moment here, M22, because it's first order, so it's not in the Navier-Stokes equation, so this is a ghost. Yeah? M300, the one that you have sometimes talked about, I think we've already derived this, that this is equal to M100. Yeah? So it has an alias. So this is an alien. And then you can actually, so aliens also have ghosts, yeah? That's not just for us. Aliens also have ghosts. M420, yeah, this is equal to M220 is a ghost and an alien. What is the name of this Israeli historian wrote Sapiens? He's talking about AI a lot, right? And he says, so this is not artificial intelligence, this is alien intelligence. Yes, yeah. Alien intelligence. So, maybe I actually claimed that we do an exercise today. If you want to have an exercise, we can do some exercise. Yeah. First very short exercise. Independent, and then a little bit longer exercise in the end. Independent moments on D3Q13. So this is because this is such a common lattice. Okay. It's a good question, so that sometimes asked by people who want to have everything automated. And I got this a lot. So, I mean, if you do BGK and you do Taylor expansions or no moment matching, you actually don't need to know what moments there are, right? But if you use your moments in the collision, for example, if you remember this picture where we can be anywhere inside this circle, and we don't go along a line, but we'll put somewhere else. So we use all our degrees of freedom. Then we need to know our degrees of freedom. Yeah, and now the question is, you look. How do we know what moments correspond to a certain lattice? And as far as this D3Q27 was concerned, my answer would be, you look, you see. Right? No. I mean, so for me, this is obvious, what moments there would be on that lattice. So if you start pruning, it becomes less obvious. Yeah? So, but let's see. Do we think that we can have a moment M000 summing over all the populations on this lattice? Yeah, we think so. So, can we have moment 100? No?
Corners, we are anti-eliminating corners.
So why is this? No, there's no problem with corner. Yeah? So now we would have 3 of these. So M110. So this is a problem. See, this is a problem that they had with the initial lattice gas in 73 or when it was, because they didn't have the corners in 2 dimensions. So there was no moment. Yeah. So if you compute M11 on that lattice, because you have to multiply f by its direction in one direction and the other. So you see, if you don't have the corners, then they will always be 0. So if you compute this moment, they will always be 0. However, this is a moment that appears in the Navier-Stokes equation. Yeah? So then you see your discretization does not support that moment, Meaning you cannot solve the Navier-Stokes equation without that moment, the hydrodynamic moment. This is required. And this is possible in D3Q19 because we have the edges. Yeah? We have the edges. So, and out of this, we have 3 permutations. Then, M200. Now, this is like a non-brainer because it's one dimension, so we have opposite moving particles. We have 3 permutations of these. So, do we have the third order ones, like M210? So what do we need for having them? I mean, we were talking, so we are just missing the corners, right? Is missing a corner here a problem? See, we have one of them is 0. One velocity is 0, so we don't end up in a corner necessarily, right? So we can do this with the edges. So we have these guys. So we have 6 of these. And also, now, this here, for the same reason, 3 permutations of this. And now we do the counting. We have 1, 4, 7, 10. So actually, okay, 10. These are the hydrodynamic moments, the 10 hydrodynamic moments. Then we have 6 and 3 is 19. Okay, so these are the moments for D3Q19. And this is why look and see. Is look and see a good solution for this? Okay, we come to another solution to this. Yeah. Problem is, apparently there is no simple way of doing this in general. Then the question, somebody has done this. The thing is, we don't need to talk about usually this a lot because this needs to be done only once. So in science there's so many things that need to be done only once and then it's good. Then it actually doesn't matter how expensive it was, right? Yeah? So the way this was done, and maybe it's not, and this is sometimes in some of these automated code generations, they may try to automate this, but I'm not completely sure that this is always successful because there may be some nuances here. Yeah? So how this was historically done. So what we do, we take an arbitrary enumeration. People like matrices. Are you guys liking matrices? Okay, me not. So, okay, we get then we do an exercise later with matrices. Yeah. So we take an arbitrary evaluation of our populations. See, I like Miller indices. Yeah. A matrix, you always have to decide how they are ordered. I don't have this problem. That's your problem, not my problem. Yeah. So it's arbitrary enumeration of populations, so that we have only one index, F alpha. with alpha being an element of 1 to q, where q being the number of the number of velocities in that velocity set. Yeah, and all of them have the velocity that has three components: e alpha x, e alpha y, and e alpha z. Yeah, so this is the vector of their velocities, and this has to be specified with the ordering. Yeah, so no other way. So then, if out of this you intend to calculate the raw countable moments, then you have M, A, B, C. You can still compute them by summing, now only over one index, alpha, yeah, from 1 to q, F alpha, and now you have this E alpha x by the power of A, E alpha y by the power of B, and E alpha z by the power of C. Okay? And now we will have F alpha and this thing here. So this this is a product. There's no comma. Yeah. So this is E alpha z by the power of B and this by the power of C. We will express them in terms of vectors so that you can do your linear algebra on them. On vectors. So, and now this comes into the Pra and Ket formulation. So the Pra-Ket formulation, I believe, is due to Dirac, I believe. Yeah. So, and this comes from quantum mechanics. So, I mean, you see, nobody started their life with Lattice Boltmann. So this was introduced with by people who were previously doing other things. And these guys were doing quantum mechanics, and this guy was doing crystallography, okay? So I use crystallography to describe this, and they use quantum mechanics to describe this, yeah? Both is misuse of, but anyway, yeah? So the way they do it is we define a Pra, that's apparently a Pra. So Pra is a way of writing a vector with this function P of A, B, and C that we define as E1. Okay, I hope I have enough space here. So this is now the index of these vectors. Yeah, by the power of A, E1 y by the power of B, and E1 z by the power of C, and comma, and this is going on into E, so the last one is EQ. Yeah, EQ x by the power of A times EQy by the power of B, and EQz by the power of C. And this is how we close the Pra. And the Pra is connected to a Ket, and the Ket is the populations, and this is usually the Pra is apparently a lying vector, and the Ket is a standing vector. So that's I'm not a quantum mechanics guy. So you have all your populations in this Ket, yeah, and then you can simply use this here. So this is because this is a moment generating vector. So you get, this is how they like to write this. MABC is this Pra with this function, so with the moment generating, it's the moment generating vector. and this goes into the cat. And this is the definition, Dirac's definition of a scalar product. So you get one term out of this. And this term will be the moment. So now what you do, and we can now, if you want to stay here, we can do this as an exercise. So check if P, A, B, and C is linearly independent of all lower order vectors so meaning that okay, what I mean by lower order, so this is, so A plus B plus C must be smaller than A plus B plus C. So it's independent, then we have an independent moment, and otherwise we have a dependent moment. And now we have to do the choosing, which, if you have a good lattice, can be done almost automatic, and if you have a difficult lattice, it becomes probably a little bit more problematic. So if it's not independent, we have an alien moment. We have a, what is it called, a meeting of the third kind also. So, do you want to do this? You want to do this, okay? Then what we are going to do, now I have to change a little bit gears. So in order to do this, we use something that is kind of a little bit connected. So we are going to use Mathematica here. What is your familiarity with Mathematica? I teach a course on Mathematica in the summer. It's not coming up. Yeah, okay. Maybe this is, I don't know, maybe artificial intelligence will actually kill this. So this is the old-fashioned style how all of this was developed. And I made the mention that Stephen Wolfram is, you see, this is Wolfram Mathematica. So Stephen Wolfram claims that he invented Lattice Boltmann. He has written one paper in the subject. Okay? But admittedly, it was the second paper that was actually published in the English language. Previously, we had some French ones that actually proved that this is in French, is coming out of France. It was not necessarily very visible. So, later when we go on to actually write the real Lattice Boltmann code, we also use Mathematica. Usually you should not use Mathematica for actually coding, but if you develop a method like this, you have a lot of equations that you have to deal with. Yeah, so you do all the preparation in a computer algebra system, and of course you should use a free computer algebra system probably. There are a few. I'm an old-fashioned guy. I can't use them. I've just learned this, and this is what I'm using for my calculation. So maybe artificial intelligence helps you to translate all of this into what is it, SymPy or whatever. Yeah. Okay. So what we are going to do as an exercise is to try to find the independent moments for the D3Q13 lattice, because they are a little bit more complicated. You remember the D3Q13 lattice only has the zero velocity and the edges. Yeah? So, but we'll do it a little bit general. Let's say we try to do it general. And we see, okay, I make this larger. No, I don't. Okay. So I have a little bit cheat sheet function. So it's actually I found out it has some yeah. It was not the solution that I was expecting. Okay, so what I'm going to do is, okay, the way we come to these lattices is usually we start from a full tensor product and then we do pruning. So we cut out things. So there are different ways of how we could do it. I just do it now this way, that okay, maybe step by step. Yeah, so we generate a table. I'm never writing this correctly. So table is, again, how familiar are you with Mathematica? This is a way to generate an array, right? Yeah. So, and I will have this as f as a function of the indices I, j, and k. You can also write this with indices, but I will now write it like this because it is easier to manipulate. And we are going to fill this from -1 to 1. Yeah? And doing this for j and for ij and for k. So, okay, from -1 to 1. Okay, now we get this list of lists, and because we want to have this in one list, we can use in Mathematica, we can tell them to flatten this, and then we have it in one list here. Okay, and then so we have a list of all the 27 directions. Okay, I'll set the semicolon to get this out of the way. So what I like to do in order to generalize this so that we can reuse this also for the others is I'll extract the different energy shells. Yeah. So energy shells is when we have the same number of indices, obviously. So because in the diagonal we have a higher energy than we have in the direct. So I'll identify now, even though this may be stupid, I'll identify the zero energy shell, which has only one element. And we can do this here by taking this all f and just select, we take all f, and out of this we take the ones where the indices of this thing here, or the arguments in this case, sum up to 0. Yeah, and this this we do by lambda functions. I believe lambda functions now become more common that I don't need to explain these. So a lambda function is we apply to all the components. Yeah, we apply this lambda function, and this will take the argument, so the component. Yeah, so this is indicated by this hash, and this function can be treated, because everything in Mathematica is a list, can be treated as a list. Yeah, so we can take the first argument of this, which is which would be here what we have in I, the second would be j, and would be k. Yeah, so that would be the first. So we check the first, and just to get this more quickly done, because we're interested in energy shells, I will take the absolute value of this. So, and then we sum them up, in their different directions. So meaning we'll look at the second index and the third index. And then we have to tell Mathematica that this is a lambda, that there's something wrong with the, yes, with the brackets. I guess it's starting here to be wrong, right? Yes. So the way we tell Mathematica that this is supposed to be a lambda function is by setting this this operator. I don't know. I find this confusing. But so we get nothing. So why don't we get anything? Yes. Why? Because I did not check that this is 0. Okay. So. Now this, so how many energy shells do we have? We have 0, so we have the center, we have the faces. So that would be 1. We have the faces, this is when we have energy 1. Oh, I'm not sure I should have, otherwise they multiply these. Yeah, so this is always with 1. And then we'll have the edges, right, thank you. The edges come with 2. Maybe I should call these, should I call this center? Other name, yeah? Center, face, edge. Okay, and I continue with the corner. So 3 is corner, and then we are done. So, okay, so these are all of them, right? So if we want to have, okay, now one thing first. We want to compute our moment vector out of this, because you like, I just learned you like matrices, yeah? So I'll define a moment vector. So this takes as an argument the populations F. So we have here these wildcards in order to indicate that this is actually an argument, yeah, and not a name in Mathematica, if you're not completely familiar. And we have A, B, and C. So these are the indices of our moment, yeah? And we define this as a function, so lazy evaluation. You know what lazy evaluation is? No, so this is, so you're not using Mathematica a lot. Only a little bit. So lazy, yeah. So in summer we have a Mathematica lecture if you want to join. This is important for functional programming. Yeah. So if you want, so this is so it will only be evaluated when you call you come to call it. Otherwise, it will be evaluated. So these things here are evaluated immediately. This is eager assignment, and this here is a lazy assignment. And there's lazy. So there's many cases where you have to distinguish between lazy and eager, whether it's executed at once or executed later. Yeah. So for functional programming, that's a pretty important concept. Okay, now what we do, we use the map function also for functional programming. Map function comes from Lisp, I believe. Yeah, is Lisp still alive? I don't. So the map function, what the map function does is it's applying a function to all elements in a list. Yeah, and in Mathematica the list comes in the end here. So I'll have a comma in front because the list, and here I have to specify the function, and the function that I specify is again a lambda function. And this lambda function now will be that again we take the argument of this f, yeah, which is ijk, and say this is the first argument by the power of now a, not writing in French, but times the second argument by the power of b times the third argument by the power of c. And this is a lambda function, so we have to specify that this is a lambda function. Okay, so now we've defined this function. Now we can actually try this out. No, we cannot try this out. First we need, okay, now we decide, right, so we have to decide of our velocity set. So we take D3Q13 velocity set. So how do we build this? So what do we need? Obviously, for this, with shells edge, yeah, I start with the center first, yeah. So this is what happens. No, leave me. Go away. I'm in a lecture. Right, so we do shell center. We do shell center first, and then we do shell edge. And that's all that we have for D3Q13. Yeah? So, first of all, when we do this, we get, of course, a list of these lists, but we want them all in one list, and this we do again by flatten, as we've just learned. So, now this is our D3Q13 list. Yeah? And now we want to have a moment vector. Yeah? So we take moment vector of now our D3Q13. And what do we want to, okay, we want to have 0, 0, 0. Oh. Why didn't this work? Very annoying. Now I can check whether you were very, very carefully listening what I said last week. Okay, that's difficult, but I remember I mentioned it. Any idea? What's the problem? I mean, they say what the problem is, 0 by 0. So where is this? So here velocity 0. You take 0 to the power of 0. Mathematica doesn't like this. So last time we said, so we define that 0 by the power of 0 is, okay, I don't, the way I'm going to tell I'm sure that there are other ways of doing this, but I'm quick and dirty. I'm doing it like this, okay? I just add something, and actually I believe Mathematica is doing this wrong. And I'm always waiting, what version is this? Is 13.2. I think we are much further than that. I'm not updating regularly. Okay, I'm doing something that's potentially wrong, yeah, but will work anyway. So this will work anyway. Yeah? So now let's try another moment. Now we have this stupid AA here. So the way of getting rid of this, and this is kind of annoying that this actually works, is we can do a substitution in the definition of AA and substitute this by 0. So the good thing is, now it depends, and this is why we use lazy and eager definition. Yeah? With lazy and eager you can steer which one is first and which one is second. But here we are lucky. They will first evaluate this and then do the substitution with AA equal to 0. So when we do this and do this here, we actually get a nice vector. Okay? So now that's now our velocity. So actually what we can do now is to make a list of our, so in order to know in which direction what works. So usually if you look in the paper, the way they show you what direction is what is usually simply done like this, because the ordering is arbitrary now, right? So you just generate these vectors, and now you see that the zero, the thing in the 0 direction has no velocity. The one in the first, oh yeah, okay, so no. We are mathematically, this is not the 0 one, this is the first one, yeah? So the first one has velocity 0, 0, 0, right? So it's the one in the center. So then the second one has -1, -1, and 0. So it's, that's the edge that's going in minus x direction and in minus y direction. Yeah. So here you can identify where it's going. Yeah. So and now we want to determine what moments we can isolate, what independent moments we can identify. Okay, I suggest that we do this semi-manually, yeah? So identifying them by hand, because there's questions whether this can be easily done, completely automated. But then you think about cases, and I know that there are codes that do this automated, but they only distinguish between very, very clear cases like D3Q, so that you do this for all the cases automatically, because you actually have choices. That you may have choices. Yeah, that's a problem. There is not a unique definition of this. But let's try to get started. So say we start from this here. So by the way, how do we see now whether these things here are linearly independent? Because this is what we want to know. See, this is actually a matrix, right? Easier. So from, we can calculate the rank. Yeah? So, that's basically, we are using the functionality that's implemented in Mathematica to make our life simple, right? So, matrix rank. Matrix rank of this, and what do we have as an outcome? That all of them are independent of each other. Okay? So now these are just the velocities. What we have not yet included is the mass. Yeah? So, I mean, the conserved moments on that lattice are independent of each other. Great. Yeah? So, now we need the hydrodynamic moments. So and there are 10 of them, four are conserved. And so what is the next one that you like to have? I probably use the copy this. So which one is the next that you want to have in your matrix?
We can do the above one that we did for getting whole list, the list of all the things.
The list of all the things.
Yeah, all the, we can directly and the table, and then we can flatten that to get all the 10.
You want to have a table of the moments. Okay? Okay, so you explain how to, okay, so you want me to, good, okay, I have not prepared this, but there's an exercise for you. So we want to have, so, okay, you have to dictate, so because I don't know what you want, you have to tell me.
So for the second order movements, we know the ijk would be like, would be in the order of 2.
Well, you want, did I get this right? You want to have a table
Which will have all the the second order moments that we would want to calculate.
all the second order moments that we want to calculate. Okay, how do we count? I mean, like there are not so many second order moments. I believe it is easier to write them down than to write a program that writes them down. Yeah, I mean, of course, you're right. If we come to very, yeah, but I think in this case it still deserves that we write them down by hand. Yeah, I mean, we can use copy and paste. So second order moment, which one do we start with? I mean, there are 6 of them, obviously. Yeah. So, okay, I'll just do it. Yeah. So it's 2. So another one like this, and then we have the diagonals. Like 1. Okay, the diagonals. So these are the diagonals, and we get 10, and by this we have all the hydrodynamic moments. The rest are ghosts. The problem with ghosts, they are not gone. You still have to define them. So what ghosts do we take? 1, 2, 0, okay? One, 2, 0, 10, 11. Okay? So then, what else would you like to have? One. Okay, now, you know, dealing with moments is an exercise in geometric imagination. Yeah? Think about 1. 1, 1, 1 means there is, you need to have the velocities all non-zero, right? And you only have the edges. On an edge, there is one direction always 0. So if I put, look, what happens? This is, if we don't know, then it's great we have Mathematica, yeah? 1, 1, 1. So what is the outcome of this? Yeah, because we have only edges. So we need something else, not 1, 1, 1. Permutation. Which? Okay, now you tell me which permutation. So how many permutation does this have? How many moments do we have left? Only 2. So how do you permute? This is a real lattice with, this morning I looked it up. Actually last year there was a paper on this. But I think there are probably 10 to 15 papers on this. This is not a commonly used lattice. But you can use this, and yeah, you can have an exercise trying to implement Lattice Boltmann with this. It's a challenge, but interesting. So what, you give me one permutation. Yeah, give me one. 0, 1, 2. Ha! So.
Maybe 1 a 0 in the middle.
0 in the middle, okay.
Yeah.
1, 1, 0, 2.
2, 0, 1.
2, 0, 1. Oh, great. So okay. So what was the thing? So you get, you're changing the 1. So you have 1 here, 1 there, and 1 there.
It's really the circle. It's a permutation, not
Permutation circle.
exchanging, just circular permutation.
I hate this. This is really not good. You got 3 out of, you get arbitrary 3 out of 6. By the way, does this get arbitrary 3 out of 6?
Any 3 of 6 will work.
No, you just noticed that not.
Just numbers not working.
So you had some that didn't work.
And then this is also this circular permutation.
Yeah. Okay,
Oh no.
I tell you, you could potentially. Okay, so there are a few reasons that we have not yet. Okay, there are reasons why this doesn't work like this that we have not yet discussed. So this moment would not work. This model would not work in that setting. Yeah, but for reasons that we have not yet discussed. Yeah, because now we just look at the at whether we can make them independent or not independent. So I wouldn't like this, and even though I don't know whether this is done like this, so could be your exercise. So if you don't want to do the homework that I've prepared for you, I would rather try to take all of them into this and add here the what is this? So actually this would be director's cut, I would say. Let me see. Still 13. So I have the differences between all of them included. So this would be my intuition, but not quite, because there's a problem with this lattice. I mean, we can also this is actually the thing that I wanted to show, and I wanted to stop here. But there is this lattice does not support a BGK, and the reason why it does not support BGK is because this would generate an anisotropic viscosity. And there is a way to repair this, but this cannot be done with this basis. So in order to repair this, we need a little bit of different basis. And okay, I'm just the basis that we would have to change is here in these second order moments. Yeah. So they need to be distributed in another way. Actually, they would rather look like this. We have to isolate the isotropic part of this. That looks like this. So this would be the isotropic part. And then we take the anisotropic part, comma, so where we take the difference again of this, and the other option is, so there are several options that do the same thing, yeah? So I've just rearranged the same vector in a different way so that we have an isotropic part and two anisotropic parts of this. And this still is supposed to have 13 independent vectors. Now, the problem with this D3Q13 lattice, or one of the problems with this D3Q13 lattice is that due to this restricted number of degrees of freedom, it's not easy to adjust the third order moments correctly. So the speed of sound appropriately, such that you get an isotropic viscosity. So if you don't have an isotropic viscosity, what you can do is that when we study this harder, we see, or when you think about the transformation of a tensor, yeah, and you have the direction x square minus, say, z square, and you rotate this by 45 degrees, you actually get a vector like this. So, okay, you see what we I don't know whether I can potentially draw this. No, I believe this is the wrong one, right? How is it done? Okay, so as a postscriptum, yeah. So we'll talk about this in a later lecture. But say you have this here with plus, plus, and you have this here with minus, minus. If you rotate this by 45 degrees, you get plus, plus, minus, minus. Yeah? And this is the rotation from x, so x or x square plus y square to xy. Actually 2xy, but yeah? But you see, you can transform the one moment to the other. This is in a transformed coordinate system, and this is also the reason why you need these diagonals. And if they do not behave in the same way because they have wrong speed of sound, what you then need to do is you have to assign different relaxation rates to these different moments. And this only works if you isolate the isotropic part. So here, with this lattice, you can only simulate the Navier-Stokes equation if you give different relaxation rates to these different moments, and then this is why there is no BGK possible for this, but still you can use this for simulations. Okay, this was more than I wanted to say. You are here again. Yes, I will now stop the recording.